So a big chunk of our activity here is research, and a big chunk of our work here is in instruction, but we don't have a lot of opportunities to hear about the very active research that goes on the instruction side. So I thought it'd be great to have an opportunity to hear from somebody who's very active in that. So you may not know, of course, there are departments of education, but there's a specific discipline of physics education about how to approach and teach physics specifically, and Professor Atkins Elliott is an expert in that. She got her PhD in physics at the University of Maryland, and now is an associate professor with a joint appointment in physics and education at Boise State, and researches questions related to how to teach and educate in physics. So she'll be talking about some of her work on that. She's authored 2 books, co-authored a book, a textbook on biology with a biologist to try to make it more connectable to concepts of physics, as well as a book about physics writing and science writing and science communication. So today she's going to tell us about seeing like a physicist, and very happy to have you.
Thanks. Thanks for having me out here. So my usual, perhaps if you looked at the announcements a few days ago, you saw a different title on teaching for transfer, which is, I usually speak now with education folks. I'm kind of, most of my time is in an ed department. These are the conferences I typically go to. Transfer is a huge problem in education. We've gotten pretty good at being able to teach a particular concept, assess for it, understand whether or not students get it. But whether they'll ever actually use it again or notice it again when they need to use it is still a thorny issue. So teaching for transfer is a big idea in that field. But what I don't often get to title it as, but I can here, because seeing like a physicist is less important to education writ large, is what it is to have taken a physics class and then go out in the world and see the world in a new way on account of having taken physics. And so I don't think that's going to be something that's hard to convince you of, that this is a thing we might want to do, that physicists do have a way of walking around the world and seeing physics all around them. But I wanted to start off with my own story. I have one interactive part of the lecture, because it's kind of required if you teach education. Then it'll be over to hear your examples. But my example was, as Neil said, I was a grad student in physics. I was at the University of Washington when I started. I was in a large house of grad students. 5 of us decided to do beer secret Santas, where we'd pick each other's name from a hat and then give each other beer. And so 5 of us drew names. No one drew their own name. And someone said, well, what are the odds? And I was like, yeah, I feel like every time I do Secret Santa, the first time you draw your own name. And of course, what are the odds is not a rhetorical question to people in the sciences. So we thought about it for a second. No one could come up with it quickly. I was in advanced quantum at the time, so then I started thinking of symmetry factors and all the ways in which you might draw names. And so then sketched out on the whiteboard for my colleagues who are also in physics. These 2 would be the ways that you could have 5 people draw Secret Santas and not actually draw your own name. There are 20 ways to draw this arrangement, 24 ways to draw this arrangement. And so, of course, then 44 out of 120 ways to have, right? So odds were that we would not draw, that someone would draw their own name on the first try. In fact, what's even funnier is this is approaching 0.368, which you might recognize as 1 over E. And in fact, after 2, you would never do 2 Secret Santas with 2 people. It wouldn't be a secret. So after 3 people, you're already at a third. You're already getting close to what it's going to be in the limit. And E shows up here. And I put this on the board. Someone in the house recognized what I was doing, thought it was funny. We talked about it. We figured out the 1 over E thing. And I live in a world, you live in the world, where doing Secret Santas is an opportunity to do physics. You get to see different things in different ways. You get to recognize, I mean, seeing E show up here, to me, is a little bit like, you know, you're hiking in the Antarctic and your best friend shows up. It's like, what are you doing here? That there's value and meaning and joy in being in the world as a physicist. And I think if you were to walk through New York with a historian, with an architect, with an entomologist, you would see the world through their eyes too. And that would be fascinating. But I love this discipline. I love being able to walk through the world as a physicist. And that's a thing that I want for my students. Something I won't talk about in this presentation, but it's important enough that I want to mention it first, is the importance and the value for me of also having people to share it with. So living in a house with people who also enjoyed talking physics is another opportunity to do physics. And in some of my studies of students, it's students who have close intellectual confidants, is what we call them, who they can share their intellectual ideas with after they get home at the end of the day, also are much more likely to have these kinds of experiences in their science classes. But Anyway, so this is my goal for science classes, is that students can leave physics class seeing and experiencing and finding joy. So as I said, my one interactive part of this lecture, as much as we're supposed to be interactive, I actually usually hate being told I have to talk when I go to a colloquium. But just turn to your neighbor. I'm just curious if you can come up with examples from your own life where your physics, and not as part of your work, right? Of course you do physics all day as part of your work. But while walking around, like, so last night I'm falling asleep, I cracked the window an inch, and it was loud, and I was like, if I crack it 2 inches, will it be twice as loud? No, what's going, right? Like, you just start playing these games in your head. So if you have examples, take a minute, share them, and then I want to hear if there's anything super exciting. Pause now. One thing that's just interesting to notice is how many gestures are happening. Like, we also don't talk physics, we use our hands a lot when we're imagining physics ideas. But did anybody want to share out one that was particularly fascinating? Okay.
I'll share one since I invited you. I feel like I have to.
Yeah, sorry.
Whenever I am making coffee or tea for my wife, I have to think about when she's going to drink it and what time I want the temperature to be at the right temperature. And since the heat loss is proportional to the delta of the room temperature and the temperature of the tea, and I decide whether I want to add the milk right away, so it'll stay warm for a long time, or whether I want to wait till the last possible minute to add the heat so it'll cool off quickly, so it'll be drinkable quickly.
My husband, who's also a physicist, and I, when we were doing classical mechanics, did the, if you drink coffee at a constant rate, what's the ideal shape of the coffee cup for that? Anyway, so we play, playing physics is fun. And so I'm going to call this intercontextuality because other people do. And it is when this context, it's essentially E showing up when you're playing Secret Santas, right? It's physics ideas showing up when you're making your wife's coffee. So doing Secret Santas, right, is an opportunity to play with ideas from advanced quantum, and it adds meaning and value and joy to these everyday opportunities, everyday moments in my life. I want to say a reasonable goal for a physics class is that students could have such moments. Working in K-12, where really very few of them are going on into scientific careers, I think it's even more critical for this as a goal. So moments when you could see the world as a physicist might. So this is one of the things I'm interested in, and I have a grant to study. I have a colleague, Brian Frank, who is a co-PI on this grant with me. And when you're researching people, you have to give permission forms. And he warned me that when I hand out the permission form to my students and say what I'm studying, which is, do you see and notice and value and use your physics ideas outside of physics class? He said every time he's told students that, they laugh. I was like, that's interesting. So I walk into the physics class to tell them this.
I'm studying if people use physics once they leave the physics class.
And of course, they all laugh. This is a class of engineers. They're all going to be scientists, or engineers someday. But not only that, very serendipitously, I think, I'm aimed at this table, which then has the following comment.
The air drag caused by me riding my bicycle causes my air hairs to deflect while hitting 13 degrees. We don't have toward my neck.
So on the one hand, we know he's joking, right? Like, you can tell voice, everything. It almost sounds like the Simpsons scientist. But there's something interesting about what he imagines. Like, he cannot imagine that a scientist, like, people actually go out and see physics around them. If he tries to, this is the best he can come up with. And I'm going to talk later about, I think there's actually wisdom in what he thinks a physicist could possibly wonder about all day. On the other hand, so I teach future elementary, or at the time I was teaching a future elementary school teachers class. These are undergrads. You're going to see they're mostly women because that's the demographics of elementary ed. Most of them do not like science and have not had much success in science in the past. And the reason I started this grant was because I was noticing they were talking about it differently than students in my physics class were. And so when I asked them the questions on the survey saying, do you see, notice, value, use, there's an option for a free response, and a student writes, well, right now, our group is working on the idea of how glasses and contacts change the shape of your cornea, maybe to balance out a person's misshapen cornea. We thought we could explain it by explaining that people with nearsighted vision need glasses with thicker glass on the sides. People with farsighted vision need glasses with thicker glass in the center. However, we only knew what nearsighted glasses looked like. We didn't know what farsighted glasses, like reading glasses, looked like. When I was at Walgreens the other day, I saw reading glasses. I decided to investigate, and sure enough, glasses were thicker in the center. As the intensity of the prescription increased, so did the thickness of the center. I was so proud of our group to turn out correct, which is not only like fascinating and right, I think it is the kind of thing a physicist might find themselves doing. So a little outline of the talk. The thing I'm interested in are these like symmetry factor moments. When I give this talk to non-physicists, I do flat Stanley moments, where a totally different education analogy. But symmetry factor, so if I say flat Stanley, I mean symmetry factor. Moments when our experiences in physics class inform and add value to our out-of-class lives. This is called transformative experiences. How do we measure these moments? So I'll talk a little bit about the survey and the results. And then looking in on classes that have high incidences of that. And it could be that the literature right now should say these are classrooms that support far transfer. What I'm going to argue is a different way of thinking about transfer, which is something education people care about. And then why is it so, what is going on in the physics class that they laugh at the very idea of it, and implications for that? So I'm drawing on work that others have done in education called transformative experiences, which has been described as notice, value, and use. This is Kevin Pugh's work, and tries to imagine that as a holistic noticing, valuing, and using happening. It's a theory of experience that comes from Dewey. But he argues that first, like, there has to be this expansion of perception, which is what I mean by seeing like a physicist. I can't help but see situations in terms of this new thing I've learned. That it has to be valuable. It's not just you do it, but you enjoy it. I find that, so students would say, I find that this knowledge makes my out-of-school experience more meaningful. And motivated use. So it's not just that someone has asked you to go do this as homework, but I find myself doing this in everyday life, whether people have prompted me to or not. So when I take this survey and I give it to our future engineering, or our engineering students, future engineers, these are their results. There's 31 questions ranging from in class I do this, out of class I do this without even being prompted. I'll show you the questions in a minute. But so this graph, they're all unit 1 in length. The dark green is people who strongly agree, dark blue is strongly disagree. And so we see this is pretty typical across all the physics classes I've looked at for future scientists, where most of the time they're saying, half the class is saying no, not really. Some of the times they're saying yes. The literature prior to this work on transformative experiences suggests that it is more likely to happen for students who have a strong identity in science, who see themselves as scientists and who are pursuing careers in science. So this should be about as good as it gets outside of a physics major, because these are future engineers. When I've given this to the future elementary ed majors, it looks like this. So overwhelmingly, it's an entirely different class, right? This is almost apples and oranges, except for the fact that they're now saying questions, seeing physics all around them. So questions like, I talk about this just for the fun of it. In fact, before I started giving this survey, I had students come in saying, my boyfriend said he's going to break up with me if I say one more thing about how high works, right? I've used this even when I don't have to. So students, like I was at we study the eye and vision. It's like I was at the movies the other day and I was like, I bet that projector is just an eye working backwards, right? I can't help but see things in terms of this. This one is fascinating to me. This knowledge is useful in my everyday life. You would think an engineer wouldn't say that about physics. And that an elementary ed major who actually doesn't teach light in the eye wouldn't. And then I pay more attention to it now across the board. My students are saying yes and no. And the ones where we're seeing the physics or the engineering students say they do, it's the questions that are like, during class I think about this topic. I mean, they're even disagreeing with that, right? We know there's certain like, during class I use this knowledge, during class. So those are the ones that are the highest for both groups, but those are the ones that, that show up for the physics majors. I mean, the science majors as agreeing. So the first thing I want to do, which is more of a statement for folks in education, is to construe what is happening as a moment of transfer, of taking an idea from one context and choosing to use it in another context. So transfer is one of these holy grails of education. So this is a free choice transfer. And then you can tap into, there's been meta-analyses of transfer. It's something people in cognitive science, psychology, and education all study. And the one consensus statement is that far transfer across strikingly different contexts is harder than near transfer. That's one of the few things we can say about transfer. And even within that, Barnett and Sessi, who do this meta-analysis, develop a taxonomy of transfer context to describe such transfer, which I'm going to use because my idea is what's going on in this class where far transfer is happening. And so bear with me as I walk through a little bit of this. So there are many ways in which you could vary context to make transfer easy or hard. So one is a knowledge domain. Did you teach them something about a mouse and now you're asking them questions about a rat? Versus teaching them something in science, like primary colors, asking them in arts. The physical context matters a lot. It turns out if you learn an idea in one place, it's a lot easier to do well on a test in that same place than to go somewhere else and be asked about it. The temporal context, so most psychology studies actually are just a day later or the same day. Years later, of course, it's a lot harder to find evidence of being able to recall the idea. The functional context, this was an interesting study where they were teaching people in a statistics class and then they called them and pretended it was a Gallup poll to see if they could still draw on their stats knowledge on the phone. Turns out no. If you know you're being taught in your physics class and you're asked about it tomorrow in the physics class, you'll probably do well. But if you're asked about it outside of that, the context, the reason why you were learning it, you're probably not going to use that knowledge. Social context matters. Did you learn it as an individual, being asked to recall, being versus in a group? And then the modality, like if you're, this one's a little weird, if you were lectured about wood carving then asked to carve wood, that's hard. Whereas if you're using the same modality, it's a little bit easier. So then we can look at Maddie's the student who was at Walgreens. We could look at what she's doing to kind of see how far her transfer context is. Her name, my colleague Maddie's here, it's a different Maddie. So, right, she's using ideas about science to make inferences about science. So I'm not going to argue that the knowledge domain, it's not like she was using it to choose the glasses she was going to buy, right? So it was transferring from science to science, not really transfer. Physical context, though, you could say is pretty different. Not many students you would think about science when they're at Walgreens, very different place. The temporal context, several days, since we've talked about it in class. The functional context, academic work versus being out shopping. The social context in a group, we did this all in lab groups in my class versus being alone, so it should be far. And the modality at school, she has a lab notebook and a board and all these things to work with, and here she just has this display of glasses. So on the one hand, and I'm gonna challenge this actually, is that the literature right now says that this should be far. This should be a weird thing she's just done, very hard to have happen. I want to instead say that maybe, okay, she was doing science in class, she starts doing science in Walgreens. But maybe the physical context, what mattered so much wasn't whether she was in Walgreens or not, but that she had glasses. The glasses define the context for her. It's like if you're shopping at Target and you see a soccer ball and you start playing soccer with it. It's not that weird, it's a soccer ball. That's eliciting that for you, not the fact that you're at Target. The temporal context. This one's a little harder to argue. Several days have passed, but to me it's as if she was reading a book, put it down, and picked it back up. But there's this beginningness and endness to our work that's going on here that makes this a little bit more seamless than you might expect. It's like meeting up with a friend from college and you just pick up where you left off in a way that I'll say more about it in a bit. The functional context, she's actually, as soon as she sees those glasses, she's not shopping anymore. She's actually doing the lab investigation that she wanted to begin earlier, and she's just finishing it there. The social context in a group versus alone, she says she's coming back, she's going to tell her group, and she's going to imagine they're to be really excited that they turned out to be correct. She has an imaginary audience for her work while she's there. So, and then the modality. In class, she was imagining this hands-on, they wanted glasses, there was a thing she wanted to do, the glasses show up, she's able to do it. So it's not so far, here's my optics, or my visuals. So traditionally, we might think of this experience as far transfer, but I want to argue it's actually really near transfer. And that what we think of as as context is a lot more malleable than we think. And I'm going to borrow a quote from someone else on similarity, which I think also applies to context, is that the perceived similarity of situations is malleable, not fixed by objective properties of the situations themselves. Well-designed activities, so education, can alter the perceived similarity of situations. So as what's dissimilar situations can become similar to one another with learning. And to me, this is the way every physicist sees something as a spring. The number of things we see as similar changes because of how we've learned to see the world. And so there are things that we do in our classroom that promote this idea of things that seemed not the same to suddenly become the same. There are things we can do in our instruction that allows the outside world not to be so divorced from what's happening in our classrooms. And at least for Maddie and this experience with Walgreens, but actually across the board in this class, these opportunities come up. So the example here, this is when thinking about transfer across functional contexts. So this is what people in cognitive psych call breaking functional fixedness. So if you give people, the classic example is you give them a matchbox and a candle and and a thumbtack. Say, can you mount the candle to the wall? People don't recognize that they can just use the matchbox itself as a ledge. There's functional fixedness to the objects in our life that we are not likely to use them in ways they weren't intended. And within the classroom, glasses broke functional fixedness a lot earlier for students. That, to me, is where the moment happened of allowing this later transfer to happen. So usually, right, when we do labs, the lab equipment in our classrooms is very much its own thing, right? You're not going to see these objects and artifacts of the traditional undergrad physics lab outside a physics lab, which actually limits students' opportunities, I think, to see and notice physics in the real world. This is the whiteboard from their work. They were worried about near and farsightedness. But so the claim that I make with this study is that when students invoke other contexts in the classroom activity in scientifically consequential ways, so when the ideas that they're developing are accountable to out-of-classroom contexts, this could be particularly rich for fostering what I call transformative experiences or transfer in particular and transfer more generally. Which is, let's see, okay. So my little image for that is that it? Oh, we'll see in a minute. Supposed to do something else. All right, so we're going to visit a classroom and see how does this happen, what's going on in the classrooms that seems to support this. How do we start leveraging and bringing in out-of-classroom resources into our conversations? And so in this conversation, students start my class, sometimes we start by dissecting this class on light and color. We start by dissecting an eye. This semester, we started with pinhole cameras and trying to figure out how they work. One set of students has come up with the idea that light must bounce off of something and go in all directions in order for a ray to enter our pinhole and make an image on the screen, which you'll recognize as diffuse reflection. It's a correct idea. But we're going to hear from a student doesn't think this could possibly be right. And we'll hear her explanation and the ideas that it invites. As you're listening to the student conversations, consider the range of contexts that come up in the conversation. And that's what I'll be noticing and talking about in a little bit.
I was thinking about it too, because like, if light's reflecting off of the desk, like say that's what we think, wouldn't we be seeing it as like a shiny brown, like it'd look like the desk was kind of lit up, like in the cartoons where they get an idea and the light bulb's kind of like fuzzy. So wouldn't the desk be all fuzzy brown and the chair would be all fuzzy yellow, not just yellow and brown? It wouldn't just, you know what I mean?
Like
So-
it would be like almost like a glowing neon.
Exactly, it'd be glowing and nothing's like glowing when you look at it.
It's just like a small glow. I don't think the whole object would be like, oh, because there's a lot of light hitting it. It would just be like little, that's why we see it. I feel like reflective things are more of the noise, and that's why we see it. But like, none of these things are reflective. Like, we're not reflective, so that's why it's just like, oh, like little ohs around us. Do you get what I'm saying? Like little objects. I don't think the whole entire thing's gonna like glow. I don't think that's how, I don't know.
Like, has anyone ever seen like a dance performance or like Broadway or something? When the stage is all dark and like there's a spotlight on one person, that person appears to like, they have like a fuzz around them of like where that light's like hitting them, because like, I don't really know why, but like I've seen, like I danced for like my whole life, and so like watching the tapes back and everything, like the person it has like a fuzzy glow around them when there's like just the spotlight on them. And like, because I feel like it's the same idea as like the moon in space, like when everything around you is like dark and you're the only thing that's like reflecting that light, or like fragmenting that light, whatever word we want to use for it. Like I feel like that has that like, oh, around you.
Right. We've been debating whether light scatters or shatters when it hits. So she's been using the word fragmenting. If you heard that at the end, it's another debate that was going on. But to kind of recap so the first student has written on the board what we want to think. Somehow light goes out in all directions when it hits a surface. It should do this for our pinhole theaters to work, right? And so Alyssa's concern is it doesn't look like it's glowing, right? And in fact, she's positioning a chair as evidence in the classroom. Chairs are not usually in physics labs, part of the evidence you're collecting from physics labs. And she's saying it should be fuzzy, right? Does that make sense that if it has, so this way of drawing light is reflecting off in all directions is exactly how we've been drawing mag lights making their light or the sun making its light. And she even says it's like in the cartoons. And it's true. Like, if you want to show something is glowing in a cartoon, you draw light rays emanating out of it. It has a fuzzy edge. If you want to dress your kid up as an angel in a Christmas pageant, right? You put feathers on them because this fuzzy edge is how we show and represent and think about what it means to produce your own light, to glow instead of just to reflect. And then I say, yeah, it's not like a glowing neon light. She's like, yeah, that chair is not glowing. This idea can't be right. So I didn't show this, but Janelle, the person who sings, pokes a little mag light through the paper to say, I think it is doing this. It's very small, this glow that comes off. We can't see it, but it is not a pew-pew. In terms of it's still reflecting, but in this weird way. I think there's something to us using everyday objects in the classroom. I mean, we use the one thing they have to buy for the semester is a mag light. We use mag lights in paper. She also starts singing about it, which is an interesting representation to me. But we kind of know, I think I know what she means when she talks about like specular versus diffuse reflection in this way. And then Google Images helped me find this. Here's someone dancing with the lights on them on stage. Yes, in fact, they do look like they're glowing. And this is, and then the final thing she says is it's like the moon, right? If everything around you is dark, you actually do seem to glow. And it's crazy because now we're like, this chair is actually a glowing yellow light, right? The only reason it doesn't look like it's glowing is because it's not the brightest thing in the room. And so if we think about the range of context being brought to bear in this like 5-minute conversation, the range of knowledge domains that are positioned as relevant and important for making sense of physics are knowledge about how we draw things, knowledge from dancing, knowledge about neon lights. The physical contexts that show up in their conversation are comic strips and the moon, neon lights, dance performances. The temporal context, so the Goldstone and Malinsky quote, in that paper they describe what education should do is to tesseract things from the Madeline L'Engle book, Wrinkles in Time. So like to bring things that weren't similar close together and make them similar. And throughout this class, they don't know if they have the right idea, right? There's an open-endedness to our questions and our conversations that they're trying to figure out the answer. And this open-endedness allows them to consider things that happened a long time ago as relevant and things that will happen in the future as possibly relevant. They're suddenly thinking about the times when they viewed dance tapes or read comic strips, and also the function of the moon. So there are many different kinds of other functional contexts which are suddenly relevant. Social contexts, different social contexts are brought to bear. And it's very, very multimodal, right, this kind of conversation. We're drawing on cartoon representations, we bring in mag lights, we talk about videos, they sing, and they're bringing in their whiteboards. And so the argument that I'm making is the outside context showed up in the learning itself. It's not our transfer anymore if what happens during learning is transfers to everyday life. And I can't anticipate in advance. It's not like I come in and I'm like, does anyone remember when they were dancing? And there's a bright light on you, and it had this kind of reflection. There has to be space for the students to bring in their own ideas and to remember things from their outside lives. So that's the broader argument. I also think there's an everydayness to this conversation that almost seems like you can imagine sitting around a table and having these conversations with friends that debate this idea. So the thing that's surprising to me and that I wonder about is why is that so rare in most physics classes? So I presented data from a different class, but a similar kind of conversation. And one of the questions from the physics audience was like, so how do you get them to care? Like, clearly they care about this answer. They're having this conversation. How do you get them to care? And I was like, how do you get them not to care? It's physics. We all love physics. And afterwards, he came up to me and was like, Leslie, that was a serious question. And I was like, it's a good point. So I decided I would go and decide if physics lab students find very boring, they don't like going, what are we doing in those labs to make them not care? Because I think that is as much what's happening as what's happening in here to make them care. And what I'm going to argue is that in most of our classes, there's something going on called the implicit contract. This comes from a math education person, Brousseau, which I think of as how do we get them not to care? We were talking about this a little bit at lunch today. And it's throughout education that what I expect you to put in your lab write-up will be and will only be the things that I cover in lab. I'm not going to ask you to draw on data from somewhere else in your physics lab. What's on the exam will be covered in lecture. What I tell you is only right. When we're done on Monday, we're going to build on that on Tuesday. We're not going to go back and revise. Whereas in this class where I teach, you never quite know. The students are generating the ideas, and so we are constantly going back and revising them. And this leads to what Engstrom calls an encapsulation of learning, that what you learn in this context is useful and valuable only in this context. It's very self-contained. We don't make references to outside contexts. He even says, so his study was why people, students after learning about the moon, actually aren't able to make any reasonable claims about the moon. And he says what they study isn't the moon, they study a textbook. And so often, and that's what he calls an encapsulation of learning. So often we're just studying the lab. We're not actually studying the actual thing. So this implicit contract is actually pretty, and I was saying this at lunch today too, it's pretty reasonable, right? It seems like a fair thing to do, but in reality what it winds up producing is that the teacher's intention is no longer the student's understanding, but the student's success. And Brousseau, who writes about this, he's French, and he refers to a play about, it's a math professor or a math teacher in France who has a student, or no, not a math, just a writing teacher in France. He has a student, and he's trying to get him to spell correctly. So he's giving him a spelling exam on, I guess, mouton is how you say sheep. Mouton is how you also say the plural of sheep, but you spell it differently in France, right? Like if the plural has an ES on the end, even though it sounds like the singular, he's giving the student this writing test. And he winds up taking mouton and saying it incorrectly so that the student will write it correctly. I'm going to play it for you because I actually went out of my way to find a clip of this.
Des moutons. Moutons. Voyons mon enfant, faites un effort. Je dis des moutons.
All right. So he's essentially taking, the argument goes, he's taking this spelling problem, which is understanding the context and being able from the context to understand that it's plural and therefore it must have an S on the end, and he's turning it into a phonetics problem. He's turning it into, if you can just understand that I'm saying S on the end, the student will write it correctly. His aim is the student's success on this exam, not the student's understanding of how to write the word without these kinds of cues. And so I'm going to argue that in our traditional physics classrooms, so I'm going to look at a lab that they happened to be doing the day that I taped in there, where the student made the joke about his beard. They're using Pasco equipment. Do you use Pasco equipment? 90% of universities or more use Pasco equipment for teaching students. And on the day I came in because they were studying light and lenses as we do in my class. And these are the instructions. So on the left you'll see there's a slit. You get one ray of light through. It hits a D-shaped lens. It's going to land on a screen. Underneath there is this lovely protractor so you can easily measure the angle. It's arranged just so that every ray of light coming in is going to hit perpendicular, so it only bends once. And so it says, the instructions are, given a D-shaped acrylic lens, experimentally determine a value for the correct index of refraction. Students will also build a fundamental understanding and implement linearization techniques. They're given this set of methods, so they're gonna set up the light source. They're told exactly what to do at every step along the way. If you've tried to get students to recreate Snell's law, you know they're gonna make a mistake, and you know looking at this how genius it is, how it's gonna solve every kind of mistake a student's gonna make. It's even put the protractor on the table for you, so students don't have an opportunity to make a mistake in even determining what angle they're going to measure. And at the end of the day, what students turn in from their lab, they're told to plot sine versus sine instead of xy. So they're even told to plot something that should give them a straight line. They're told from that slope they should be able to find the index of refraction. And then at the end of the day, what they have to turn in is their value for the index of refraction. What I want to suggest is at the end of that, of course they're going to think, my beard hairs deflect approximately 13 degrees towards my neck. Why would anyone care about what the index of refraction of light is, how we're determining it? These lenses, we don't use D-shaped lenses for almost anything other than pedagogical purposes, I don't think. We don't have protractors that look like that. Everything within this is so self-contained so that students can come up with the index of refraction for acrylic, that of course they're going to think that what physicists do is match bizarre numbers to other artifacts for I don't know why. And so at the end of that lab, of course, they're gonna think that what possible opportunity is there? Within the class, as I'm taping, I'm listening for when do they recruit ideas from out of class? Are there any moments when anything outside of physics class has come up in their conversation? The answer is no. Most of their conversation is which equation should I use? Is this lined up right? And then why are we graphing sine? Well, it says to. And so the opportunities to bring in context from outside of class are just not there. And trying to imagine how the student would leave this lab and then notice and see and value and use those ideas outside of class where they won't see any of these objects is a little hard to imagine. So in my class, I'll just show you, because they do wind up wondering essentially about Snell's law. I do have a box of prisms in the pack. They do grab the one that looks most like a cornea, and they have their lasers pointing at it to try and figure out which one bends more. You might see they're squirting dry erase board cleaner to be able to visualize the rays as they go through. So some things are going to be sacrificed, right? They don't ever get to Snell's law. They get to the idea of the steeper the angle, the more it bends. They understand, like, they're surprised that a lens can have such a perfect shape that it bends them all back together at the same point, and that no matter where it came from. So they wind up, just a brief aside, no, not a brief aside, I'll step back a lot. So in this class, we've started right by dissecting eyes, trying to figure out how it is that we see images. And one of the early ideas that came up this semester from a student was this idea that was really profound to her and became important for the class, that the world isn't made up of images, right? It's really tempting to think when you see a door that there's an image of a door flying through the world to land on your retina. And she's like, actually, I think we live in a world of Seurat spots. That it's like a pointillism world. They were taking their elementary ed art class at the same time. That we just live in a world of Seurat spots. And the other student comes up with this idea of light fragmenting, except this semester, which is different from the one I showed. He decides that these Seurat spots are actually half disco balls that reflect light off in all directions. And so the light fragments when it hits, sends off in all directions. And what a lens must do is construct a Seurat spot reunification point on the other side of the lens. And then they debated whether or not they should call it a Seurat spot reunification point or the Seurat spot reunification plane. But because they had the same acronym, they could agree. To disagree, we would just call it the SSRP, where these images wind up being reconstructed. The fact that they get reconstructed in a plane and that there is actually a shape that will do that for us and that our eye makes that shape is phenomenally exciting when they get to that point. So they never actually come up with N1 sine theta 1 is N2 sine theta 2. But I think they can talk about it in a lot more sophisticated ways than most of the students who do have that kind of background. And so in terms of what's sacrificed when we teach this way, I think the hardest thing, the nice thing about my class is that they're elementary ed majors, so they're not going on, this is the one and only physics class they'll ever take. I don't have to worry about preparing them to walk into someone else's class where Snell's law is a given and that they know n1 sine theta n equals n1 sine theta 2, n2 sine theta 2. I don't have to worry if they know how to use Pasco equipment because they're not going to go teach in high schools. I don't have to worry about any number of things because this is not a prerequisite. They're not going to have their exam for becoming elementary school teachers doesn't even cover this topic, so I kind of can let them leave with whatever they want. We get where we get, and every semester we get to something different. So this semester, the idea of all of these points mapping into a plane became incredibly critical of how it does it and what that shape must be that it produces that. In another semester, and I talked to the students about this earlier today, one of my students said that for Surratt spots, right, to come back together, if we want to have them magnify, it has to be blurry because we must be getting further apart. They must be getting bigger. If we were to magnify an image and these spots didn't get bigger, if they all came back to an actual spot, then we'd have gaps between the spots because there just aren't as many points on a small plane as there are on a big plane, right? And so there are, if you know about the size of infinities. So we actually took a day and there's a very simple way of proving that the number of points on a small plane and the number of points on a big plane are actually the same number of points. And so different semesters, right? So I've had students who leave this class and then come back and work with me in the class, and they'll say things like, well, when are we going to talk about the size of infinity? Like, well, this semester it's not coming up, so it's just not going to come up. Whereas other semesters will be, well, why aren't we going to talk about Surratt spot reunification point versus plane? Or other semesters it's going to be this fragmentation idea. Different things come up different semesters, and I can allow for that in a classroom that's not a prerequisite for another class. So those are the kinds of things that get sacrificed, I think, when teaching this way. It's particularly important for me for future elementary teachers, though, to be able to teach this way because their prerequisite ideas are pretty small in terms of what they need their students to know before going on to high school, and so they do have more opportunities to pursue students' ideas and go down different rabbit holes and dead ends as they do their work. And so a summary of these ideas then, that seem like a physicist can, and I think should, be a goal of science instruction. I think it's something that happened for people who went on to pursue careers in physics. I think for us it did happen, right? That when we were taught something, we did check it with our everyday experiences. We did start looking around and seeing the world in new ways. But for others, it's very rare. And the reasons I think it's rare, one is this implicit contract everyone has in instruction that focuses on student success with particular ideas, which limits, I think, engagement in science more broadly. Classes can leave students with incredibly weird ideas about what it means to see like a physicist because of that problem, because of our labs that are so tightly focused on finding Snell's law. But I do think you can design for it. And this goes against some of the findings in education that suggest that you have to have interest, you have to have motivation, more background knowledge is better in order to have these experiences. That I think that the more we design classes that allow for opportunities to draw on their own out-of-class contexts in constructing ideas, the more we allow for wrong ideas as part of the pursuit of getting to right ideas, the more they wind up leveraging their out-of-classroom ideas in constructing their ideas, and so then the more they're able to see those ideas in out-of-class contexts. And then last, you can assess for it, which is, I don't mean assessment like I'm going to give them a grade whether or not they've seen it. I'm not going to say you don't get an A unless you've been transformed by my class. But in assessing the power of your instruction, it is something that we're good at measuring now. We're good at figuring out if it's happening for our students, and we can alter instruction if it isn't. And so that's what I would leave you with. And so then last notes, the people to thank. I work with Angie Little, Brian Frank, Irene Salter, and Kim Jackson. Irene Salter's a biologist who convinced me I could really dissect an eye in class. Kim Jackson, and we're at an ag school, so there are plenty of eyes to go around, it turns out. And then Kim Jackson is a colleague, so I've done a lot of work on how students learn to write and construct ideas in this class. One of my arguments with writing is if most of the writing you as a physicist do is on a whiteboard, then most of the writing your students do in your classroom should be on a whiteboard, right? But the ways we construct ideas in the discipline should dictate how we teach writing in the discipline. The students, super grateful for the willingness to play along with me, the funding agency, and then thanks to NYU for inviting me out. Happy to be here.
Questions?
I'm wondering, do you see this as something that needs to be sort of once does a student undergo this transformation and then you can forget about it afterwards because it'll be automatic? Does it need to be continually reinforced? And if the former, should we just be changing what happens in K-12 so that by the time they come to college they can...
So I'm not going to let you get off the hook by pushing it back on teachers before you, because they actually have a lot more constraints on what they're allowed to do than we do at the college level. So I think it'll be a lot easier for you to change things here than to ask K-12 to change. It takes a great deal of time to move that wheel. So I had a student who, so at Cal State Chico, kind of the rule in California is if you have the credentials to graduate high school, you have the credentials to get into college. And so we kind of accept anyone who graduates from college except the one degree is nursing. Not anyone can become a nurse, and so the nurses have the highest GPA. And so she got into Chico, but then couldn't get into the nursing program because she failed out of her science classes. She took my class, she went back into nursing, had a 4.0 GPA, and she attributes it entirely to, I learned how to learn science in this class. And Brian Frank, who teaches this at Tennessee, has a similar examples with his students. He has someone who's like, reading this physics textbook is now like picking up a magazine. I love it. So I do think for a lot of students, this kind of, and David Hammer has evidence, he's at Tufts with his students, that this kind of epistemological shift, once it happens, is pretty sticky. I wouldn't say all students, but I would say the vast majority learn how to learn science differently by having done this kind of work.
Does that also sort of imply that one can come up with a single course that could be part of bigger programs where you don't have to do the other part, but you just get this one course right, you've done the right thing, and that'll propagate through?
I would think so. So when given the opportunity, so you asked earlier about at lunch about remedial courses, and I was trying to say, I think within a context it works, but just saying, that students need to learn how to do X, Y, or Z better to be able to play the game of science, I would say they just have to play the game of science and learn it within that context to be able to do it. It's resource intensive for me. So in terms of this is a class that meets 5 hours a week. They turn in a paper a week. I give them detailed feedback. Someone asked me once, like, how do you have time to do that? And I was like, I teach a 4-4 load and have a research program, and I can do it. So you can do it too. And then I had a kid. And I don't put nearly as much time into this kind of course as I used to, but it is I've co-taught it as much as possible. So it's a resource-intensive course for 24 students. It's not your intro GE course, but yeah.
So if I came in here already thinking that labs are dumb, like that anything where you get a lab handout is not how science is done.
Right.
But most of our courses aren't labs,
No.
right? I mean, most of our courses are lectures. So is there a takeaway here for that?
The fact that they use hands-on material here, so let me see. I'm trying to decide, is the important thing that they were using tangible objects or not, is to me the biggest difference. Is that fair to say? Like what you can do in a lecture versus what you can do in the lab?
I mean, well, I guess what I'm saying is, okay, great that's using the acrylic wedge is not going to teach you Snell's law, right? Which I never had any doubt that that's a terrible way to learn Snell's law. Right? And even in the way we phrase the labs, we have the goals more as like learning error analysis, and it's sort of problematic because all the errors are controlled.
Yeah.
But anyway, when I teach Snell's law, I teach principle of least time and lifeguard running on the beach and trying to get through the water and stuff, right? But I mean, would it be better for them to, instead of doing that, to sit there with a piece of acrylic and a laser?
I think so. I mean, so it depends on the student, right? Like we were students, probably almost all of us, because you can't step off the train in physics and get back on very easily. So I imagine we were all students who did the kinds of wondering and hard work when someone lectured to us to make sense of the ideas. And I think if a student knows to do this, which is essentially Alan's question, if a student knows to do that, they'll get that out of lecture. And I've had students say at the end of this course, I wish all courses were taught this way, and I say, they are. When someone gives you an idea, your job is to make sense of it, hold it up to what you know in the past, try and make sense of it, look at shadows, whatever it is, to do that kind of work. That the lecture is there to give you the things to chew on and make sense of if you know how to do that work already. When students don't know how to do the work, and how do you invite them in, and how do you position these, like, what is Snell's law the answer to? What kind of vexing problem did this, why is this a breakthrough that you need to know about in this class? I mean, in the class where I teach, one semester they became really obsessed with, like, what does it mean to measure an angle with a surface that's curved? And none of them have had calculus, right? Maybe not even much geometry. But then started thinking about, well, maybe if you were an ant living on this, it would look flat, it would look like the Earth, maybe everything actually is tiny, you know, like, they developed those ideas. But they got to the question themselves, in a way, if that makes sense. I don't know if that's a good answer, but I think there are ways, so I lecture. I think there are ways in which lectures can be a lot better at bringing students into the problem, having them explore solutions to the problem themselves before giving them the answer that helps support this. I think for a lot of students who become good at this kind of thing, they don't need it, and then it can get old. Yeah.
One of the things I like about coding projects for students is that in debugging them, they need to ask a whole bunch of questions. For myself too, if I want to learn something. Is there in education for computer scientists, is the hurdle different because they're already having to ask questions as they debug their code or something like that? Or do you see that as a potential gateway as well?
Let me rephrase your question. Is there, in writing code, you already have to do this work. Writing code demands that you think carefully about each step, and you can't debug without having said, this step does this step does this. And so you almost are doing this kind of work if you're coding well. And so then the problems in computer, I don't know enough about the problems in computer science education, for one. I do know, let's see, and so would they have, I think there's a fascinating study of teaching students physics by teaching them how to code physics. So that instead of teaching them Hooke's law and then making them solve equations with it, they have to program something to do with Hooke's law. So they have to decide, it moves, it feels a different force, it feels a different acceleration, it has a different change in velocity, it goes to a different point. It moves, and they iterate and they can walk through that, and they wind up with a much more mechanistic, model-based idea of physics by having done the coding. And it's very different than this algebra-based physics of balance and equilibrium, they'd say. So that does seem to support learning physics, learning to code physics. That's a great answer there.
So you took this example of a class where you don't have to reach any point because it's not a prerequisite, but of course a huge fraction of the courses we teach are prerequisites, and you have a responsibility with the students to leave knowing X, Y, and Z. So what do we do in those circumstances?
Yeah, I don't know. I think one of the bigger findings from physics education research is that a lot of student difficulties are around epistemology, are around what it is to, what kinds of things physics knowledge is supposed to be about, what they're supposed to be doing in class. We do these learning attitudes about science survey, the CLAS, Colorado Learning Attitudes About Science. They come in actually with pretty great ideas about what they should do if they get a problem wrong and how to learn and how to, by the end of the class, they're actually answering less like a physicist. So there are things we do in our classes like this. So I think that labs are very ripe for changing. There's been a lot of work showing that whether students take a lab or not affects their knowledge of physics not at all. Looking at universities that had lab as optional. So labs are a place where I think you can do that work without affecting student outcomes in other areas. For me, another big question is, right now we're very tied to the idea of conceptual development through our courses and making sure you know A before B before C, but we haven't done that work with epistemology or attitudes, or like, it could be that we've been wrong to say that these are the important prerequisites for a course. So we can rethink that. And then I think if you notice it, like, this course isn't that hard to get up and running. Like, this is an option if you have to do remedial courses for students. This is the kind of thing one could do. But I haven't. I'm going to be teaching an actual intro physics course in the coming years where I play with this idea and see, like, how do we meet these learning targets while still having students play the game in the right way. But I don't think we have great answers for that.
Questions? All right, I think there's a reception down over on 8, and let's thank Leslie again.